Welcome to Talk Tensors. Thanks for joining us for another deep dive into some really interesting machine learning research.
Fun to be here.
Today, we're tackling a paper that gets right to the heart of federated learning security. It's all about how vulnerable your data might really be to these things called gradient inversion attacks.
Right. Federated learning has this great promise, right? Keep your data local, stay private.
Exactly. But this research asks a tough question. Even if you only share model updates, these gradients, can someone still figure out your sensitive info?
That's the crux of it. Federated learning is huge now, especially for sensitive stuff like health data, financial data, because you don't share the raw data itself. The idea was that gradients, these sort of averaged updates, were safe enough.
But maybe not entirely safe.
Well, this paper we're looking at, exploring the vulnerabilities of federated learning, a deep dive into gradient inversion attacks, really puts that assumption under the microscope.
It sounds pretty important then. It systematically checks if an attacker, just by looking at gradients, can actually piece together private data.
Precisely. It's a critical question for the field.
Okay, so before we get into the nitty-gritty of this paper, maybe give us a bit of background. What led up to this? Why the focus on gradient inversion now?
That's a good starting point. Initially, everyone was excited about federated learning because, well, the data stays put. That's a big privacy win, obviously.
Seems straightforward enough.
But as things developed, researchers started asking, what information is actually hiding in those gradients? Are they really anonymous?
Like a data fingerprint almost?
Sort of, yeah. Early studies hinted that maybe gradients weren't quite the black box people hoped. Think of it like tasting a cake. You don't see the recipe, but you might guess some key ingredients, right?
Like so.
Gradient inversion attacks are just a much more sophisticated version of that tasting the cake idea for machine learning. The concern grew that these shared updates, even though they're not raw data, could still leak specific features or patterns from your local data.
So this paper steps in to really measure how well these attacks work in the real world.
Exactly. It aims to give a much more solid experimental grounding. How effective are these attacks, really? What makes them work better or worse?
Right, so it's not just theory, they're putting them to the test. What was the paper's main goal then? What did they set out to do?
Their main aim was a really thorough analysis and evaluation of gradient inversion attacks, or GIAs. They spotted a gap, lots of attack methods proposed, but not much systematic testing to see, how they stack up against each other, what their limits are.
So filling in the blanks.
Pretty much. They tackled it in three main ways. First, a big review, categorizing all the different GIA types out there. Second, tons of experiments testing these attacks in different realistic federated learning setups.
Yep.
And third, based on all that, they proposed some practical defense ideas, ways to design FL systems to be more robust. They even set up a public GitHub repo, awesome gradient inversion attacks, to track ongoing research.
Oh, that's useful for the community. So this categorization, what are the main types of attacks we should know about?
They broke it down into three main buckets. The first is optimization-based GIA, OPGIA.
Okay, optimization-based. What's the idea there?
It's kind of intuitive, actually. The attacker gets your gradient. They start with some random, dummy data and calculate gradients from that. Then they tweak the dummy data over and over, trying to make its gradients match the real gradient they receive from you.
So it's like playing hot and cold with data until it looks right gradient-wise.
Yeah. That's a good way to put it. Iteratively adjusting until the gradients match up as closely as possible.
Okay, what's the second category?
That's generation-based GIA, or GEN-GIA. These use generative models, like GANs you might have heard of.
Using AI to make the fake data.
Right. Instead of tweaking raw dummy data, they might tweak the input code, the latent vector of a pre-trained generator, to get it to produce data that matches the gradients. Or they might even try to fine-tune the generator itself.
More sophisticated? Are there different flavors of that?
Yeah, the paper mentions a few subtypes. Besides tweaking the latent vector or the generator parameters, there's another approach where the attacker trains a whole separate model, specifically to invert the gradients, basically. A model that learns input gradient, output private data. But that has its own requirements.
Got it. And the third main type?
The last one is analytics-based GIA, or ANA-GIA. These are often more direct, trying to mathematically recover the input data, sometimes even perfectly.
Mathematically, how does that work?
It often involves the server being a bit sneaky, maybe even malicious. The server might modify the model architecture, stick in extra layers perhaps, or tweak the model parameters before sending it to the client device.
So they set up the model specifically to leak information when the gradients come back.
Exactly. They try to structure the problem so the gradients essentially give away the answer, your private data.
Okay, those ANAGIAs sound potentially quite nasty if the server isn't trustworthy. So the paper categorized them, but then they tested them. What did they find out about the first type, the OPGIAs? How well do they actually work?
So for OPGIA, the findings were really interesting. On one hand, it's the most practical in a sense. You don't need special models or server tricks. You just need the gradients.
So easier to attempt.
Yeah, lower barrier to entry for an attacker. But the flip side is its actual performance in recovering data, often quite limited. And it's really sensitive to various factors in the federated learning setup.
Like what? What makes OPGIA struggle?
Several things. Batch size is a big one. The paper found that using larger batches of data for local training significantly degrades the attack's ability to pick out individual data points.
Ah, safety in numbers, literally.
Kind of, yeah. Also, image resolution. If you're dealing with high-res images, forget about it. The attack performance drops off a cliff. The paper even has a theorem linking the error linearly to resolution and the square root of batch size.
Wow, okay. What else?
The model's training state matters. A well-trained model, one that's already learned a lot, is harder to attack this way. The gradients become less informative about specific inputs. Network architecture, too, more complex networks are generally tougher to invert.
So complexity helps privacy here.
It seems so. And one more, maybe slightly surprising finding. If you have multiple data points in your local batch that share the same label, like several images of cat, that also makes the attack less effective. It seems to increase this similarity between gradients naturally, confusing the attack.
And you mentioned standard practices.
Yes. Crucially, they found that practical FedAv day, where this client device runs multiple local training steps before sending the update, that standard procedure inherently provides resistance against OPGIA.
That's actually quite encouraging. Just doing federated learning the normal way helps.
It does seem to offer a baseline level of protection against this type of attack, which is good news.
Okay, so OPGIA, practical to try, but maybe not super effective, especially with standard setups. What about the GNGIAs, the ones using generator models? How threatening are they?
The GNGIAs, well, they look fancy, but the paper found they have some pretty significant dependencies that limit their threat in practice.
Dependencies of the book?
Okay, so take the ones optimizing the latent vector of a generator. They found these could only really recover the gist of the data, like the semantic meaning. They could tell it was a picture of a car, maybe, but not your specific car.
So category level, not instance level.
Exactly. And even then, it heavily relies on having a pre-trained generator that's already good at producing images similar to your private data. If the generator was trained on faces, it's not going to magically reconstruct your medical scans.
Right, the generator needs to be relevant.
Totally. Then there are the ones that optimize the generator's parameters directly. These could get pixel-level reconstruction, which sounds scary.
But there's a catch.
A big one. They found this really only worked effectively if the target model used the sigmoid activation function.
Sigmoid, isn't that kind of old school for deep learning?
It is. Most modern networks use RILU or its variants. The reason sigmoid was vulnerable is apparently due to its near-linear behavior in the range inputs typically fall into, which makes the inversion easier. So if you're not using sigmoid, that attack route is likely closed.
Okay, that seems like a major limitation. What about the third GNGIA type?
The one that trains a separate inversion model. That requires the attacker to have an auxiliary data set that's very, very similar in distribution to your private data to train that inversion model in the first place.
Which they probably don't have, right? Yes. Otherwise, why bother attacking?
Precisely. It's a huge assumption. So overall, the paper concludes that GNGIAs, while theoretically clever, pose a pretty minimal practical threat because of all these strong dependencies.
Okay, so OPGIA has limits. GNGIA has serious dependency issues. That leaves the ANAGIA, the analytics-based ones where the server might be malicious. How did they fare?
Right, the ANAGIAs. The analysis confirmed that yes, if a server actively manipulates the model, they can achieve very strong attacks, sometimes even exact data recovery.
That sounds bad.
It does, but here's the crucial counterpoint. The manipulations required are often detectable.
Detectable?
Well, if the server inserts weird layers into the model architecture, the client device can, in principle, check the model structure it receives. Hey, this doesn't look like the standard model I expected. That kind of check.
So the attack leaves fingerprints.
Exactly. There's a trade-off. To get good reconstruction, the server might need to make the model bigger or change it significantly, which raises red flags. Similarly, attacks that manipulate model parameters, like trying to make gradients really sparse to isolate contributions.
Can those be detected too?
They can also leave statistical traces that might be detectable. Plus, these parameter manipulation attacks often still need help from OPGIA methods to get the full data back, and they're still affected by things like image resolution and whether the model is trained or untrained. Untrained models are more vulnerable here.
So the very act of setting up the attack makes it potentially obvious.
That's the key finding. These powerful ANA-GIAs come at the cost of being potentially easy to spot if the client implements some basic validation checks. This really lowers their practical threat level in a well-designed system.
That's a relief. Did the paper look at anything else, maybe newer FL techniques?
Yeah, they briefly touched upon attacks in the context of parameter-efficient fine-tuning, or PEFT. That's where instead of sharing all the gradients, you only share updates for a small part of the model, like LoRa adapters.
Right, becoming more common with large models. What did they find there?
It was interesting. They found that privacy could still be breached for low-resolution images, even with PEFT. But for high-resolution images, sharing only those few parameters offered better protection.
So resolution still matters a lot.
It does. And interestingly, they observed that using smaller pre-trained models seemed to offer better privacy in the PEFT setting, maybe just because fewer gradient parameters are being leaked overall.
Huh. Okay, so summarizing the attacks. OPGIA is practical but limited, GNGA has dependency issues, and ANAGIA is powerful but detectable. What about defenses then? Did the paper propose solutions?
Yes, based on all these findings, they proposed a kind of three-stage defense pipeline for designing more robust federated learning frameworks.
Okay, what are the stages?
First is network design. Simple stuff, really. Avoid using sigmoid activation functions, as we saw. Maybe favor more complex architectures, as they seem generally harder to invert.
Makes sense. Stage 2.
Second is the local training protocol. Again, building on the findings. Use larger batch sizes locally. And definitely use multi-step local training, like in standard FedAV. Don't just do one step and send the gradient.
So reinforce the things that already seem to help.
Exactly. The third stage is client-side validation. This is about catching those sneaky ANA-GIAs. Implement checks on the client device to detect unexpected modifications to the model architecture or parameters sent by the server.
Basically, check the model for tampering before you use it.
Right. Their overall message was quite positive, actually. If you carefully follow good federated learning protocols, sensible architecture, standard FedAV, basic client checks, you can minimize privacy leakage against these known GIAs without needing super complex, costly defense mechanisms like heavy differential privacy all the time.
So good practice goes a long way. Did they mention implications for attackers, like how this research might guide future attack development?
They did briefly. The insights obviously show where current attacks fall short. It suggests future attack research needs to focus more on practical applicability, reducing those dependencies we talked about, especially for GE and GA.
Make them work in the real world.
Yeah. And maybe focus more on attacking realistic scenarios like standard FedAV rather than simplified setups. The OPGAA approach, despite its current limits, seems the most promising direction for attackers because it has the fewest external requirements.
Okay, this has been a fantastic breakdown of the paper. Now for my favorite part, novel notions. Based on this whole discussion about gradient inversion, privacy, similarity, what's a potential research idea that springs to mind?
Well, that finding about gradient similarity hindering OPGIA got me thinking. We know if gradients from different samples in your batch look similar, the attack gets confused.
Yeah.
So what if the client could proactively nudge its gradients? Before sending them, what if the client device itself added a tiny bit of carefully designed noise? Not just random noise, but noise specifically aimed at increasing the apparent similarity between the gradients of different items in its batch.
Interesting. Make your own data look more generic internally.
Kind of, like internal camouflage. The device could check, are my gradients for this batch too distinct? Could I be vulnerable? If yes, inject minimal noise to make the update look more like it could have come from slightly different data points. Or maybe even nudge it slightly towards resembling gradients from common, non-sensitive classes.
Without revealing the true class, of course.
Absolutely. It builds on the paper's findings about similarity, like their Proposition 1. The idea is the noise might not need to be huge to be effective against OPGIA, potentially preserving model utility much better than broad differential privacy noise.
So targeted confusion.
Exactly. It might make OPGIAs significantly harder without that big utility hit. Of course, the server might need new aggregation methods to handle this deliberate similarity introduction, but it's an interesting defensive direction.
That's a really cool idea, turning the attack's weakness into a defense. Got another one.
My second notion focuses on detecting those ANAGIAs, the ones where the server tampers with the model. The paper says they're detectable because they leave traces.
Yeah, the fingerprints.
So what if we used meta-learning? Could we train a meta-learner, maybe running on the server side or by a trusted third party, to specifically look for the subtle, long-term patterns of these attacks?
Not just checking one model update, but looking at the sequence over time.
Exactly. This meta-learner would observe the stream of updates or parameters round after round. It would be trained on historical data, tons of normal FL rounds, plus examples where various ANAGIAs were simulated. It could learn to spot anomalous drift in parameters, weird changes in sparsity over time, unexpected correlations between client updates. Things that signal a malicious server might be gradually setting up an attack.
Like learning the tells of a tampering server.
Precisely. Since the paper emphasizes detectability, meta-learning could automate and potentially enhance this, catching sophisticated attacks that unfold over multiple rounds, maybe slipping past simple single-round client checks. Think of inserting a malicious subnetwork piece by piece.
Wow, that could lead to like federated learning forensics or something.
Potentially. It draws on meta-learning for anomaly detection. It could add a powerful layer against advanced threats, especially if client-side checks aren't foolproof. Of course, both these ideas are speculative, need proper research. You know the drill.
Absolutely. Research required. But two fascinating notions spitting out of this paper. It really drives home that while federated learning is a great step for privacy, we need this ongoing research into vulnerabilities like gradient inversion to really build trust and security.
Couldn't agree more. It's a constant evolution.
We'll definitely put a link to the paper in the description for anyone who wants to dive even deeper. It's clear this landscape of privacy and collaborative AI is far from settled. Thanks for joining us on Talk Tensors.
My pleasure.
We'll catch you next time for another deep dive into machine learning research.